Thank you very much. Thank you very much. So I'll introduce the next speaker, who's Mark Huckvale, and he will have a live presentation from remote, and his talk is entitled Automated Detection of Voice Disorders in the Saarbrücken Voice Database, Effects of Pathology, Subset, and Audio Materials. Hello, Mark, please.
Hello there.
Hi.
I've got a terrible echo. I'm going to turn my speaker off, I think. Good afternoon and good evening, everyone in Brno and everyone else worldwide. Very nice to be here. I'm presenting this paper on the automatic methods for detection of voice disorders. And this is going to be looking at using machine learning methods for the detection of voice disorder from speech recordings. So there's a database called the Saarbrücken Voice Database, which some of you may know of. It's a very large database with many thousands of recordings from, as you can see there, 1,000 pathological speakers and 800 control speakers. And this has been used widely in automatic methods for detection of voice disorders, and in particularly machine learning methods. This database, though, is quite complicated in many ways, and it can be quite tricky to use for building an automatic classifier. In particular, there are multiple recordings per speaker, so that if you're not careful, you may end up having the same speaker in your sort of training sets and your test sets. There are also multiple diagnoses per speaker. And if speakers make multiple recordings, you can actually have different diagnoses for a speaker depending upon different recording sessions. There's considerable imbalance in the frequency of different disorders. There are many different possible disorders recorded in the database, but some of them are only available on one or two speakers. And so this, while this database is a fantastic resource, it's actually quite tricky to use for machine learning. And I think our interest was to look at how other studies have used this database and try and get a better understanding of the way in which they've used the database and maybe propose better ways of using this database. So in particular, we've looked at a number of different studies based on the Saarbrücken database. And here's a table from the paper. And just quickly, if you look at the last two rows there, E and F, they talk about two different studies. One is looking at simply an isolated vowel R and is using a convolutional neural network and a spectrogram and is claiming 94% accuracy, whereas the final row F, is using a whole load of different vowels, E, R, and U, on different pitches and rising and falling in pitch, and which you would think would give you more information about the presence of a voice disorder, and yet it's claiming or only able to claim a much lower accuracy of, say, of 83%. And the reason that must be is that these two studies have used the database in different ways. In particular, they've probably chosen different pathology subsets. They've chosen effectively different speakers in the database. They've varied in terms of not only the audio materials, but possibly how they've actually divided the materials into training sets and test sets. And so, in fact, these studies are not really comparable because they're actually potentially using very different data. So in this particular study, we wanted to replicate some previous studies on using the Saarbrücken database for automatic detection of voice disorder from speech recordings, but we wanted to do it using the same evaluation protocol. And these are the three studies that we're going to replicate: a study which used the vowel R and a convolutional neural network based on an auditory spectrogram, which is claiming 77% accuracy. A system which uses E, R, and U on different pitches, uses the OpenSMILE feature set and a support vector machine classifier, claiming 83% accuracy, and a study that uses an auditory spectrogram and a convolutional neural network called ResNet, also on an R vowel, which is claiming a 94% accuracy. And in our evaluation protocol is that rather than subdivide the database up into many different pathologies sections, we're just going to use all of the pathologies against all of the control data as our first pass over this system. And then we're going to use all of the normal data against all of the organic pathologies. And by organic pathologies, we mean ones which are related to the structure of the larynx or the neurological control of the larynx. We're going to look at all the different audio materials, an R vowel on a neutral pitch, the combination of R, E, R, and U vowels on different pitches, and also the short phrase. These are the different audio materials that are available on the Saarbrücken database. And for measuring performance, we're going to use 5-fold cross-validation, but we're going to do that using the speaker index as a key, which means that this guarantees that we don't have the same speaker in both the training set and the test set. And because there's a considerable imbalance in the classification and in the proportions of different classes, we're going to use an unweighted average recall metric, which is basically assuming that would give you an estimate of the performance of the system were it the case that all classes were equally likely. So because time is short, I'm just going to very quickly go over the features and the classifiers. So for the support factor machine method, the OpenSMILE feature analysis generates 6,000 features from each recording, and the support vector machine classifier is putting each one of these fixed length vectors into a class of disordered speech or from the control speakers. For the CNN method that's based on a neutral R vowel, we're building a spectrographic representation from the middle 1 second of an R vowel, and we're taking a spectral representation on a log scale, normalizing it, adding first and second order distances, and then mapping that to an image, which is these classifiers take a 2-dimensional image as input. And for the convolutional neural network, this is just done using a set of convolutional and max pooling layers and a final dense layer for classification, whereas for the ResNet classifier, this was using a pre-trained classifier that was trained on images, not spectrograms, just ordinary images, in which the topmost layer of the classifier is removed and replaced with a dense layer, which is then trained for this particular task. So effectively, it's kind of using some of the low-level feature extraction that you would use for image classification for the task of spectrogram classification. So I now present the results that we found for the, firstly, this is the OpenSMILE and the support vector machine classifier, and we were able to test this on all 3 types of speech, the vowel, the combination of vowels, E, R, U, and the phrase. And you'll see 2 rows there, one for all pathologies and one for organic pathologies. And broadly speaking, you can see the numbers, but broadly speaking, you're getting about 70% or so accuracy of detecting voice disorders from an isolated vowel. You're getting about 80% from the combination of E, R, and U, or from the phrase. If you just restrict the problem to one of contrasting control recordings from organic pathologies, then performance goes up a small amount. So you get to about 75% for the vowel and 85% for the combination of vowels and the phrase. Notice that this makes a lot of sense, that E, R, U, and the phrase has much more information about the abilities of the speaker, and hence you do get better performance in terms of classifying whether a voice is disordered or not. And also it's worth pointing out that our values here are not too far away from the published value in the original paper of about 83% for a slight subset of the pathologies in the Saarbrücken database. In the bottom of the slide here, you'll see a table with lots of numbers. You can look at the paper for more details. We also explored a number of different variants in terms of the features, and the things like building a gender-dependent classifier and changing the support vector machine kernel and so on. If you're interested in those things, pick those details up from the paper. Looking at the results of the convolutional neural networks based on the isolated vowel, so this is just using an R vowel, and just the first line in this table shows you the reference values from the OpenSMILE classifier, so about 68% for all pathologies, 73.5% for organic pathologies. Our running of the convolutional neural networks and the ResNet network on the R vowel gave values which are really not too dissimilar from those. So for the simple CNN system, 68%, and for ResNet, 69%. If you switch to organic pathologies only, then performance goes up by 1% or so, not as much, in fact, as went up by the OpenSMILE classifier. So what's important here is that the results we're getting are consistent with our own baseline, our OpenSMILE and support vector machine classifier, but these are very different to the accuracies that were published in the original studies. And so the next step obviously would be to try and understand the discrepancy between our results and theirs. It may be that our implementation of the spectrographic representation or of the convolutional neural networks are in error, or it may be that our particular protocol, which is very strict in terms of cross-validation, in terms of the choice of pathologies, and in terms of the performance metric, severely compromises the systems that were originally published. Just to wind up then, overall we found that if the goal is to detect voice pathology from audio recordings, you can get a performance of about 70% from a single vowel, which is very commonly used in clinical practice. If you manage to record and analyze a sequence of vowels, E, R, U, possibly on different pitches, you can push that up to about 80% or so. But also, surprisingly, that performance just from a short phrase, by short phrase we're talking about something which is about 2 or 3 seconds long, then that's actually as good as recording many different vowels on many different pitches. So that classification is if you're simply contrasting all pathologies from all control recordings. If you limit yourself to organic pathologies only, then the recall improves by about 5% or so. And that sounds reasonable because you're now talking about some kind of structural disorder or neurogenic disorder at the level of the larynx, as opposed to a functional disorder, which is simply about having an unnecessarily high or unnecessarily low pitch, or rather than something that's physiologically disordered. It's interesting that our CNN results don't replicate the previous studies. Maybe our implementation is in error. Maybe their results are strongly affected by our evaluation protocol. Looking back at the spectrographic representations of the R vowel, they really do not look very promising for distinguishing between disordered speech and the control condition. It's simply not the right kind of, I think, not the right way of representing the data to build a classifier. It's not a good input to any kind of classifier. And the other problem we found with the convolutional neural networks is that they're very difficult to train, and the systems have a very large number of free parameters, like the ResNet has something like 1 million parameters, and yet you only have a few thousand training examples. And so this is a real problem of fitting the neural networks, causing overfitting, and the systems effectively becomes too highly specialized on the training data. And this significantly affects their performance on new data, particularly when you've been very strict that new data cannot be present in the data used to train the network. Well, if you wanted any more details about any of that, do look at our paper, and I'll be very happy to answer questions at the end of the session. Thank you very much.
Thank you very much. Thank you. So see you later.